So hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar about the new simulation software TCAE. We have good news, we have more good news, and we have only good news for you today because we have spent enormous time and effort to deliver this new comprehensive engineering simulation environment called TCAE. It's based on open source and it has a substantial value cost ratio, and it will be our pleasure to show it to you in today's webinar. I hope everything works well. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments later via email or something. So feel free to get in touch with us anyway, in any case. And the webinar is being recorded, and its recording will be later made publicly available. At the end of the webinar, there will be, as usual, a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. You can find a little window somewhere in the GoToWebinar menu. So feel free to ask your questions. All the questions will be answered. Some of them will be answered right away in the webinar. The rest of them will be answered later via email or something, but you can be sure that all the questions will be answered. And now I think it's time to get to the action, right? So, okay, so I will start with the webinar speakers. So just formally, this is me. My name is Luboš Pirkl. My current job is telling the world about CFD support. And right next door is sitting my colleague, Radek Máca, who is our head engineer and senior developer. And let's check him out, okay? So hello, Radek.
Hello, Luboš, and hello, everyone.
Okay, he's really there. Radek, have you slept well this night?
Well, yeah.
I mean, last night.
Yeah, I have slept well. Yeah.
Okay,
because I was looking forward today. So, yeah.
It's gonna be infinite,
nice
right?
sleep. Yeah, right.
yeah. Okay, thank you. So it seems we are ready. So let's start showing things. So this is the agenda of today's webinar. The webinar is going to take about 1 hour. In the first part, I will give a general introduction to what has been done and what is on the table. In the second part, Radek will give a live presentation of TCAE. There will be he will show us what we have in real work with in the graphical interface, I think. And and finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime, and we will do our best to answer some of them in the webinar. And you can be sure that all the questions will be answered because your feedback is very important to us. So feel free to ask, and we'll do our best. Okay. So I guess you know us a little bit, but still very quickly, our company name is CFD Support. It was founded in 2009. It's located in Prague, Czech Republic, and at CFD Support we deal with engineering simulations. We primarily focus on development of CAE software with very high added value for its users. It's definitely high-end software, and our clients are CAE professionals who know well what they want. We are obsessed with accuracy. Accuracy is our highest priority, and besides accuracy, we are focused on automation, repeatability, and application-tailored solutions. We don't believe in general purpose code. We don't believe that any particular software can accurately simulate everything, or that anyone can simulate anything. We do believe that any successful project is a result of focus, skills, experience, patience, and dedication. And we believe in open source. Especially we believe in a combination of open source and professional support. And so far we have invested a lot of time. I think it's more than 30 many years of focused team development on top of open source to deliver these professional tools, and that's why we are being picked. So I have to say we have very strong team. We have very strong team. In the last year, we have worked hard. In a matter of fact, we have worked very hard. And when we met some difficulties, we have worked even harder. And throughout the COVID pandemic, we worked harder still. And these guys are very smart, actually, and I'm proud of them. And it's an honor for me to work with them. And I don't know how they do it, but they did it, and it's here. And I'm happy to show you this TCAE, which is a comprehensive CAE engineering simulation environment. And I guess you know that before we maintained TCFD, which now becomes a software module of TCAE. And TCFD was very successful, and what had worked so well in TCFD now of course remains in TCAE. So TCAE it has successfully merged the benefits of open source with the benefits of commercial codes. Due to the open source code nature, it's unlimited and extremely flexible. Due to the commercial code nature, TCAE has a graphical interface, it has professional technical support, it's robust, it's accurate, it's automated, it's well tested, and it's ready for use in the industry. And this is what you can see now. This is how the graphical interface looks like. The user can do here everything from scratch. The simulation can be set up, the simulation can be run, the detailed post-processing can be done in this interface. And of course, besides this graphical interface, there is also a batch mode available, and TCAE can be run by another software or inside another software. And TCAE is definitely much more comprehensive than TCFD was, and it's definitely well suited for further development. We will speak about it a little bit later in this presentation. TCAE consists of software modules that can be combined in a very large, in infinite number of combinations, I would say. And it's a system, right? It's not a code anymore. It's a system of yeah, how to work with engineering simulations. There are individual software modules. Right now, there is TMesh, which deals with mesh operations. There's TCFD, which runs CFD simulation, and there's TFEA, which is a module which runs FSI, fluid structure interaction, and structural analysis. So we will speak about it a little bit later in this webinar. Okay, it tells me now the webinar is full, so no one else can attend. So yeah, okay, it's doesn't matter. Okay, let's continue. Okay, so technically, since the last release, which was the version 1910, we have made so much work and so many little projects that we can't go one by one over it. So the list is very long. So the development process has broken into 144 different projects. Some of them were just small issues, some of them were nightmares, but anyway, there is 144 new things, and I believe it's very useful. Maybe what's more important, TCAE is much more comprehensive than it was before. It's a simulation environment rather than just a CFD code, and it includes 46 open source packages. To name the most important ones, it's OpenFOAM version distributed via openfoam.org website. There's a new ParaView, there's a Calculix for structural simulations, there's NetGen for let's say FEA meshes, and there are many other useful tools that support the engineering simulations. And you can imagine how much work have their authors spent on their development. And on top of that, we here at CFD Support have spent more than 30 many years to deliver this TCAE. So it's really a really big thing, and so much effort has been spent. As already mentioned, TCAE has a modular character, and the user can choose between TCAE modules and, if needed, to combine them with many other software pieces which are available in the market. So, for example, you can take the external mesh from Pointwise and use it with TCFD. Or you can, for example, design a pump in CF Turbo, you create the mesh with T-Mesh, use TCFD and do, for example, model analysis in TFEA. Or you can run an optimization loop, creating the geometry in cases, use, for example, Grid Pro for high-tech meshes, then use TCFD and together use, I don't know, FSI with TFEA. So what I want to say here, the total number of combinations is almost, Radek, what? Infinite, right? There's almost infinite number of combinations. There are a lot of software pieces out there, and any user can pick his or her combination to fit in his needs and workflow and resources and everything. So TCAE has a strong integration ability. It has been from the beginning developed in a way to fit any existing workflow, no matter if it is combined with commercial code or in-house codes or with another open source code. Because it has strong interfaces, it's very, very flexible to fit in an existing workflow. In a typical enterprise, the engineers typically have some existing workflow already, and TCAE is capable to fit in it, do its job, and yeah, to do the simulations, deliver the results for the user's judgment, and that's what we want. TCAE is very flexible. It's definitely ready to be used in a very complex workflows, optimization loops, cloud computing, and many other new trends going on out there. So it's definitely ready and developed with respect to the modern trends in engineering simulations. And there are many other stuff, real tutorials based on real projects we did in the past. There is trial version, there is a lot of documentation, it's scriptable, etc., etc. I'll continue with okay, this is the graphical interface again. I think there will be some other information about it later in the webinar. TCAE is unlimited. It's definitely a big thing. There are no limitations on number of users. There are no limitations on number of users, jobs or cores. There are no limitations on hardware installations. So it's very, very useful, and it can scale all your potential according to your resources. So the users can use their resources to the fullest. It's very important, and very that means really a lot for our users, I have to say. Okay, TCFD is definitely accurate. Accuracy is very, very important for us. We have clear focus on accuracy. TCAE is always aimed on particular applications, especially on turbomachinery, especially on external aerodynamics. Those are two very, very best of TCAE, and we have created many benchmarks, and we are ready to prove it that it's very, very accurate. As I mentioned before, we don't believe in general purpose code. We don't believe that some code can do all the simulations of everything, or anybody can do anything. It has to be focused, and TCAE is definitely focused on special simulations. We are obsessed with accuracy. We have done a lot of benchmarks in the past, and we are ready to show them, and they're mostly available, and some of them will be made available still. And we believe that any successful project is a result of focus, skills, experience, patience, and dedication. So it's not definitely not easy stuff. Okay. TCAE is from the beginning developed in a way to fit modern engineering workflows. It's fully automated, and it can be used either as a black box, so the user puts the data in, TCAE does its job and the user picks the results at the end, or TCFD can be used as a highly sophisticated software where all the options are open. So I would say that the beauty of TCFD is that it's the user who decides how deep to dive into the theory or not at all, right? So it's in this terms it's both. It's both black box and full scale high-end software. Okay, we definitely believe in the importance of the technical support. Support is coded in our DNA and also in the name of our company. For more than 10 years, we have supported the engineers in achieving their goals. We are obsessed with professional technical support. We have special process for it, which is powered by the OS ticket system. TCAE is natively compiled for Windows and Linux. Yeah, it's ready for a remote desktop access. ParaView, we have like two versions of ParaView. One is without OpenGL, one is with OpenGL. One is with on software rendering, the other one is hardware rendering, so you can access it from a remote desktop. Very, very useful feature. And of course, it runs in batch mode, and it can be run from other system or inside other system. So it's it's polymorph. It's a library if we want. So it's very, very useful. Yeah, TCAE includes its system of meshing. It's based on automated system on SnappyHex mesh or NetGen, and also the external meshes created in another software can be loaded. So we always leave this decision up to the user. Some users prefer automated meshing. The other users prefer external meshes of very, very high tech quality. So that's fair enough. We fully respect that. So it's the user's decision whether go for external meshes or the automated meshes. We use both, and we have good experience with both. That this decision is also always left on the user. And yeah, TCAE has strong post-processing capabilities. Every simulation that is executed in TCAE has its own HTML or PDF report with the results. The volume fields are processed if needed in ParaView, and the integral results are written down in CSV files and in the report, so anybody can find his way of visualizing the results. And also we have included a special turbo post processing, which is also very useful for turbo machinery simulations. Okay, so as you know, no software is ever finished. TCAE remains under continual development. It's always on the way. The development is users driven, so we continually gather the requirements from our users, of TCAE users. We evaluate them. We keep adding them into the new version releases. We use a special system for code development in a team which is called GitLab. Very, very useful and very powerful stuff. Okay, so what has been promised a year ago, it's now turns a reality. We have a system, a simulation environment, which is under continual development, right? In the horizontal direction, we keep adding new tools, new plugins, new software modules, and we extend it by complexity. And in the vertical direction, we keep adding new applications, new capabilities, and new high-tech methods. Everyone is welcome to collaborate, so feel free to join us, feel free to help us, feel free to tell us what you need. And yeah, we are definitely on the way, and the way seems to be very, very good. Yeah, okay, so there are some examples. I'll be very quick here. TCAE has always been great on turbo machinery applications like pumps, fans, and hydro turbines, and also compressors, turbochargers, wind turbines, and also, of course, for external aerodynamics like cars, the aircraft, valves, hydraulic valves, manifolds. exhaust manifolds, intake manifolds, of course propellers and ship hydrodynamics, drone propellers, I would say, and also the wind load of many other things, comfort and heat transfer, etc. We already did quite a lot of benchmarks where we really compared in detail the simulation results with the real physical measurements. Many of them are available, complex studies in PDF. You can see what software combinations have been used. Yeah, so I'll be very quick here. So it was the Potsdam propeller with pointwise, Francis turbine, fun benchmark with ZVVZ, turbocharger, TCFD, of course, scales perfectly. There was a Spitfire real simulation, Ahmed body, and a couple of optimization studies with cases and also with Grid Pro. And we also have tested and benchmarked this FSI function, which we will speak about it, I guess, sometime later. And this would be it. I'm not gonna torch you anymore. And here I need to click a few times, and we will ask Radek if he is available. And yeah, so I'm doing it right now. So Radek, do you think we can hand over the presentation over to you?
Yes. If you already finished, you can.
Okay. I did what I did, and I think yeah, I finished.
Okay.
So it's yours. The stage is yours, Radek. The stage
Okay.
is
So
yours.
just tell me if you when
you can say the joke. Yeah.
Okay.
You can say the joke now. It takes some time, but very I think very soon we should see it.
Okay. So thank you, Luboš, for your part. So I think you introduced the general things about TCAE. And now I would like to. You can see my screen now?
Yes, we can see it.
Okay,
yes.
okay. So now I will show you a real example. So I will not going to show you any new feature, or this is not taken as a training webinar. This is just to show you what is new and how the new interface looks like, how the modules are managed, and so I will show you basically the principles on, let's say, 4 new tutorials. So first one I will open the TCAE. So the installation is very standard, in a standard way as the previous TCFD, is the old version. So just a wizard in the Windows, or just the unpacking the zip file, or basically, yeah, the zip file in the Linux. As you can see, the interface, or the graphical user interface in PowerView, looks very similarly, but there are several new features and new, let's say, new and easier management of the cases. So let me start. So as you can see, it looks very similar, except maybe these colors are a little bit, I think it was something gray or in brown. Now it's in blue, and the advanced mode is in the gold. So maybe this is the new colors you can see here. And mainly what is new in this pipeline browser, now you can see that everything is already there. So now there is no TCFD manager to manage simulation. So everything is within one item here. And as you can see, this pipeline browser is split into three parts, 3 modules: TMesh, TCFD, and TFEA. So this is a new framework of working with TCAE. So I will load some preset example which is directly delivered within the installation. So I will go to installation in TCAE on C drive, the current version, and here you can see a few tutorials. So I will go through all of them, and on this piping system, which is some pipe elbow, on which I would like to show you all 3 modules, how they work. So I will load the case to speed up the process. So now when I load it, everything everything comes up. So a lot of windows appear because each window is dedicated to each part or to each module. So let's say I will make it a bit easier for now. So what we have, so first of all, we always need to start with the meshing part, of course. So if I unclick the T-mesh, so then we can see then there is a setting for the T-meshing, both for CFD and FEA purposes. They include, you can for example always visualize just the input to the CFD, so it's very the same as a TCFD. So either you can load the STL and set the meshing, CFD mesh here, set the meshing as usual, so using the snappy hex mesh parameters, or you can use some external mesh in different formats. So this is almost the same as for the TCFD. But now, okay, I will make it much easier. I will follow, just to follow me what I am doing. So this is the input for the CFD mesh. Yes, so this is the STL. If I would like to show you the input for FAA, so I can open new render view, visualize what is the input of FEA. It looks very similar, but I would like to just do the solid, yeah, do the finite element analysis of the solid. And of course, there is a FSI interface which can communicate one way at the moment. So it can put the results from the CFD and map it on the mesh for the FEA analysis by, for example, the forces or temperature, and so on. So first of all, we need to mesh the domain for CFD, the domain for FEA, and then we can run the simulation. The FEA looks very similar for these purposes. The input is again the STL geometry, so it's very similar to the CFD mesh, but now we do not have SnappyX mesh, but we have the NetGAN meshing tool. So basically, you just set some minimum and maximum sizing of the tetrahedras, and the meshing is done also automatically based on the input geometry. Or you can also put in the external meshes in NetGen format or in Abacus format. Okay, then the management of the meshing. So now I would like to mesh these geometries. So I can go on the top, on the first item in the pipeline browser, and basically this is now the manager of the TCAE manager, we can call it, using which we can manage all the workflow from the simulation point of view. So I will create new directory in which I will store the whole project. So let's say in my webinar case, for example, I have to write the case, and now I can run everything by one click. But now I would like to go step by step. So first we should do the meshing for CFD. Then we can do the meshing for FEA, and then run the TCFD simulation, and then the TFEA simulation. Okay, so I will click here to mesh all. So now the meshing is under meshing is processing, the mesh is creating, and at the end I can immediately show the mesh here. So here you click on the eye next to the CFD mesh and go back to the manager and click to show one of these, because these are the same. And this here we can see, if I visualize this with edges, now we can see the mesh. So it's let's say coarse mesh for the training or for the runtime purposes, to show you really how it works runtime. So this is the computational mesh for CFD, and for TFEA. So I can click here to visualize the FEA mesh, go back to the, let's say, manager, click here, show FEA mesh, and this is our FEA mesh. So this will be used for FEA simulation. This mesh will be used for the CFD. So I can, for example, show you both of them in one render view, just to see. So this mesh, let's say the orange one, is used for the FEA, this for the CFD, and internally the forces from the CFD acting on the inner part of the piping wall will be put as the input for the FEA analysis. Okay, so now it's time to run the simulation. So now let's go. I can go for the TCAE manual run. I will run the CFD simulation, and I can wait several seconds to perform the simulation. Anytime, as usual, I can show the graphs. So if you click to the TCFD, there are several items. For example, I can visualize the residuals here, and in the second line chart view, I can visualize the quantities, and in the display display part here, I can visualize, for example, I don't know, let's say the total pressure difference for the piping system. In the view, again, I can adjust the axis. So let's say use the axis, it's piping, so there will be pressure lost. So I think 5,000 pascals to 0. Okay, this is good view. Again, the standard TCFD approach, so we can simulate several points within one simulation. So if I go to the TCFD setup, so it looks very similarly for those who already used or is using TCFD 1910. So standard management, we have several points to be defined: standard fluid, multiphysics, turbulence, solver setup, boundary conditions. Here are some new features. Maybe I will show you for another example. So now we can, for example, set for each wall different boundary condition, different wall functions. For example, it's per patch, it's not per component, but it's per patch now. So similar for temperatures and so on. So this is much more easy and intuitive. Anytime you click any part of the component, it is visualized in the render view to know to which part you're assigning particular boundary condition. So I think the simulation is almost finished. Let me see. Yeah, the last iteration is performing. After the simulation is done, I can create a report, and immediately I can run the TFEA simulation. So I can run the simulation because the CFD results are already written. So TFE module can take the data from TCFD module, transform it, and map it on as boundary conditions for the TFEA simulation. Okay, meanwhile, anytime we can show the results as usual. So I can split the view. So here I can show the CFD results. If I click the show button, here we can see the pressure distribution or any other quantity which is evaluated. So this is the CFD results. So we have 3 points. So for the last point, for example, where the flow is pretty quick, and we will see how the TFEA simulation or which deformation and other quantities will be shown in the FEA analysis. So let's go here, just check if the simulation is still running. Yeah, the second point is now simulating. So maybe meanwhile I can show what can be set in TFEA, which is really new. So we have, let's say, 3 menus. In FEA analysis, which is the main part of the setup, we can see which physics we would like to model. So there is a thermal analysis. If we have a temperature information, so for compressible solvers we can apply it. Fluid structure interaction, which is for, let's say, all the cases which you would like to connect to TCFD. The source information is where to take the CFD data. So I think in 90% of cases you will use TCFD as a CFD tool and FEA as a TFEA as a FEA tool, or you can also use some external directory with CSV files, which is automatically generated, or you can generate them also in the TCFD module itself. Then you just pick from which patches you would like to take the data for the mapping. For rotational framework, you can also include the rotation. So for the turbo machinery, you can also take into account the rotation of the solid and the for example, displacement and stress analysis, which takes into account the rotation and these inertia forces. Map forces from pressure, of course. If you would like to map the forces, if you would like to use the relative pressure or absolute pressure, which sometimes can be confusing, because from one side you have no mapping, so basically 0 pascals, and from the other, if you will have the absolute pascal, it will throw you the nonsense results. So you have to keep, if you do not apply the mapping for the whole surface, so you have to always use the relative pressure. And you can also activate the modal analysis to reveal some eigenfrequencies and these modal analysis parameters. For the solvers, there are two solvers, direct one and the iterative one. You can standardly use the linearized equations of the solid state for the deformation, and you can also use the nonlinear equations for the analysis, which could be more precise. Then the materials with the Young modulus, Poisson ratio, and material density. So you can put any parameters which follows follows your material. And the boundary condition, you basically, for the deformation, you pick by simple shapes which part will be fixed. So in this case, for example, we fix one end of the piping, and we would like to see what will be the deformation and stress using this condition. And basically that's all. So it's much more easier to set up the FEA module than the TCFD. So I think the simulation is finished. So now I can visualize any result. So we have 3 points, 3 results. So I will show you the last point for which we set the highest flow rate. So the deformation should be also the highest. So yeah. So now the results are loading. Okay, so this should wait or click. Have I clicked here? Maybe I didn't click. Oh, I'm not sure now. So again, oh yeah, okay, I didn't click on show results button. So it always put into pipeline browser the results from the given time frame. So if we have more points, we can visualize any results which is connected to any point of the TCFD simulation. Okay, so I can hide here in the left render view and show in the right render view. So this is the FAA mesh, and for example, I can visualize the displacement in meters. So we can see that the displacement is something like 1.5 centimeter. What is also nice, for example, there is a nice filter which can really visualize the displacement. So this warp by vector filter can show us what is the displacement compared to the original shape. Yeah, so this is the real displacement of our current setup for the pipe elbow, which is made from some kind of rubber. And in the same way, we can visualize the displacement, the stress, the maximum stress, and its distribution along the whole geometry. So the stress magnitude, and if we have the model analysis, we can also see some frequency analysis parameters. And for both, of course, for both simulation, we can visualize the report directly here. So here I can see the report for the TCFD, and here I can visualize the report for TFEA, which I haven't yet generated. So I need to click, FEA report. So I will generate the FEA report, and it has a similar it is very similar to this CFD CFD simulation report. So it includes the basic information about the simulation, which material was simulated, about the solver, mesh statistics, how many points, elements, and so some quality mesh parameter in sense of minimal and maximal angles, and of course the static analysis, the parameters maximal, minimal displacement in each direction, and so on. And the same for the stress, of course, maximum stress and in the stress in each components, and the information is placed for each point. So the points can be connected into the points in the TCFD simulation. So for example, here the total pressure difference could be interested in this piping. So for each point, we can see the deformation of the elbow in the report of the TFEA. Yeah, so this again, this can be run automatically by one click. So this can be repeated. So we can change just the input geometry, repeat. So it can be everything can be put into the optimization loop. The same works in Linux, in bash mode, and so on. So this was the typical example how to work with all the modules. So the meshing for the FEA for CFD and TCFD setup remains almost the same, and you have a new model available using which you can perform the FEA analysis. So let me show you another 3 examples. So one example is this simple benchmark case for this. This was this beam ball, so ball which is placed on the stick, and the forces from the CFD analysis is prescribed on the stick, and we will see what is the displacement, and we compare it to the analytical solution, which is well known for the simple shapes. So again, the input for CFD is standard. So we have some kind of virtual tunnel. We can apply any refinement near our objects as for standard external aerodynamic applications. And the input for FEA, which I can visualize here, but I think I need to zoom it. So this is the ball with a stick, right? And as a result, so the results from the ball from the CFD simulation is put as the boundary conditions for the FEA analysis, and then we can also again visualize the deformation on the stick and compare to the analytical solution. So this again is the displacement, which is something less than 3 centimeters, and similarly for the stress magnitude, which is of course the maximum near the let's say point where the whole stick is fixed. So you can analyze it visually as you want, and also again inside the reports you can see everything what you need. So maximal displacement, which is the maximum, but yeah, for our benchmark we need to read read the results from the top of the stick. Yeah, so which can be done very easily. So I will just click here and I can read the displacement from this table. Okay, and the same report, of course, for the CFD simulation. So I don't need to go through the whole report. So standard parts of the HTML report. Okay, then I have two more examples. First one is the axial fan simulation. So this simulation includes the rotation. So this is the example of for turbo machinery. So again, the input geometry for TCFD. So standard segment geometry is put as the input. For TFEA analysis, there is the blade, which includes this part which manage the rotation. For example, for the axial fan. So this axial fan with adjustable rotating blades, and we can perform analysis by simulating CFD and then adding also the solid part and perform the analysis, including the model analysis in this case. So in this case, we have also here the model analysis, and we can set how many eigenfrequencies, so mean frequencies which can impose some oscillation of the rotating blades. So again, CFD mesh, the TFEA mesh is generated, and then run the simulation to get the results. So again, the pressure distribution for each point. The simulation, I think, includes 5 points with different flow rates or different total pressure differences. So for each point is or the pressure distribution is taken and mapped to the FEA analysis. So each point are simulated again, and we can compare the stress magnitude. So I think the flow rate is decreasing and the pressure drop is increasing. So for the higher ponds, the pressure load is higher. So we can see that also the stress magnitude is rising for each point with a higher pressure drop, of course. And again, here we can visualize the real displacement. So I don't know if it's visible. So the colored one is the standard shape of the blade, and the white one is the transformation, which is magnitude. Yeah, so which is high, which is forced to be more visible. So the displacement is less than 1 millimeter, and this visualization is again done by warp by vector and it's multiplied by 50. And so this is the real displacement, which is, I think, barely visible. So we can multiply this displacement to be nicely visible and see let's say the topology of the deformation more clearly. Yeah, so now you have many options how to visualize it. So ParaView itself includes many filters, which in combination of the results with CFD and FEA gives you a really nice tool for visualization and analysis of the results. And similarly, we have two reports. So I will go through the FEA reports, and what is new is this model frequency analysis. So we can see 3 based frequencies, which makes trouble, or which makes the whole simulation oscillates. Some participation factor, which is the magnitude of the oscillation in each direction for each eigenfrequency, and some other frequency parameters, which I think it's no time to describe into detail. So this is again done automatically and can be applied on any turbo machinery design. For example, it can be also applied on the centrifugal fan. So again, the principle is very the same. CFD geometry, FEA geometry, the solid of the wheel, CFD mesh, FEA mesh, run the simulation, and we can see the results. So again, the mapping is done for the whole blade, for the whole wheel, although one part belongs to the rotor part, for example, the second part belongs to the spiral part, but any part can be assigned to perform the FSI analysis, which you can do here. So any part, any wall can be put as a mapping source for the FSI. So this is the result of CFD simulation for the first point. I think you can again visualize any flow data and any filter you can apply, and then you can see the displacement, how the wheel is deforming, and of course where are the results here, and of course the stress analysis and what are the stresses. So again I think, yeah, it is 10 times multiplies the original displacement. So this one is the real displacement, which is really small. I can visualize the original shape, if you can see. Okay, yeah, so the deformance is half a millimeter. Oh no, half a centimeter. And I think the diameter of the wheel is half a meter, so it's a huge radial centrifugal fan. So you can really play now with what you want, and you have a lot of new features available to perform your analysis into more detail. And maybe last thing which is new, and I would like to show you that in TCFD, the approach to set the boundary conditions, which is really nice. So for example, for each wall separately, I can I can choose the impeller here. So per each patch, I can, for example, take the impeller pressure side, and you can see that each part is visualized here. So the similar for spiral. So for example, if I take the spiral tongue, so then you can see that you are now adjusting the boundary conditions. So for example, the standard wall function I can prescribe, and I can also prescribe the slip wall or no slip wall. So wall without friction, wall with friction per each patch in your domain. And similarly, if you have more inlets, so again you can assign per each inlet what you will be your boundary conditions. Okay, so I think it's 5 minutes to 4. So now it's time to, I think it's time to your questions. So I will go back to Lubos. So Lubos, are you awake? Are you there?
Yeah. I was all the time awake because it was very interesting to watch this from this perspective, and I like it. It was great, Radek. Thank you for your contribution, and let's keep it this way. By the way, I suggest not to hand over the presentation over to me, because there are a lot of questions. Many of them are very specific, so it will be easier if we will be able to show them live in the graphical interface. So okay, so let's move in the webinar to the last part, and let's discuss some questions. There are many questions here, so I'm absolutely sure. Yes, exactly. Yeah. I'm exactly sure that we cannot answer all of them, but let's take a few interesting questions that may speak for more people, and yeah. So if you Radek, if you see one, you can answer them.
I haven't time. Okay, for example, I see one
sure.
which is
so I can start.
Is TCAE based on F finite volume method or finite element method? Okay, so the TCFD module is based on the finite volume method, and the TFEA module is based on finite element method. So
yes.
both methods
it's
are
open
used each for each module, right?
Right. right? It's OpenFOAM, and for structural analysis we use a Calculix. So it's Calculix. So all the information is easily searchable. What else? Heiko says, "Wow." So what does it mean? I hope it's compliment, right? It must be a compliment, sure. Okay, there are a couple of questions from Matthias. Hello, Matthias. Yeah. Can you add new material properties to TFEA? Well, you can definitely add material properties, but not the question is if, for example, the temperature depending. So not, I think not directly. It would be that certainly would be a matter of discussion. If it's not possible, I guess it's not. We would definitely be able to edit, or I think in general I can say if something is not there yet, I'm sure we'll be able to edit very quickly, because these guys here are unstoppable, I would say. So yeah, so the very much technical questions are difficult to answer, because I don't know it right away. The same answer is about
I can just say
okay.
few things here, that the temperature can be mapped, right? But some advanced temperature materials parameter cannot be set via graphical user interface. But I think Calculix has some feature of that, so it can be set by scripting, I guess. Yeah. So the temperature can be mapped. Yeah. So we count with that. So for compressible cases, you can map also the temperature and some advanced temperature parameters, depending. I think if Calculix includes, it can be used by scripting option to set them.
Okay.
And in the future, it can be implemented into the GUI. Yeah, that's true.
Great. Yeah. Shankar is asking whether is it possible to animate the results. So can we make my favorite
Okay,
an animation?
I will try some simple example. Okay, let me show you this, for example. Okay. Okay, it can be it can be, yeah. So I can create an animation based on any parameter which is here. So I hope I have many window open. So I hope the animation will be visible to you. So yeah, here I have the animation view, so I can add the new parameter to the animation. Let me see. Okay, here. Okay, new one. 0. Okay, apply, and let me see. Okay, maybe I have too many. All right. And now if I run and save the animation, so I will try to run it. So you will see. I don't know if you see anything. Maybe it's not.
Not much. I think it's not that important. Okay.
But yeah,
there are definitely, yeah.
It is possible. Yeah, right.
Yeah. I have a couple of questions about multiphase. I'll be honest here. For example, Rasoul is asking. I'll be honest here. TCAE, it is a good example. TCAE doesn't do multiphase simulations, because we think multiphase simulations are very difficult. I mean, VOF here and Euler and these things. It does multiphase actually in the cavitation modeling, but these VOF and Euler, we don't think it's accurate at all. And what's not accurate, it's not for us. So we leave it for other people, for other tools in the market. We do classical single phase modeling, which is accurate. It can be measured. It can be really it's tangible. It really works, and we do what's accurate and what works. So TCAE is not for multiphase, I would say, VOF and Euler simulations at the moment. Maybe in the future, perhaps maybe we will start a new a new project on it, but not, we did not do it yet, and it's not even behind the door. Okay. What else? There are so many questions, and we are already running 1 hour and something. So Radek, do you see any question you would like to answer? There are many, really many of them. Don't worry, we will answer them, but still not there yet. Can't make it here.
Okay, I can see one question. How does TFEA cope with non-isotropic materials? So I just show where
Yeah.
is it? Material properties here, isotropic, and we have also orthotropic, so we can set parameters in each
can play around
direction as a tensor, right? So, or as a vector, right?
Yeah,
so
wind turbines are a good example, right, of this orthotropic material, because it's definitely not rigid in all the directions in the same way.
Yeah. So we have orthotropic in this option in the FEA module.
Yeah. Okay, Radek, what do you think? I think we should stop here. Maybe
we will
this would be
answer all the question after webinar, just not to bother too long, right, the audience, and we will answer all the questions afterwards. Yeah.
Okay. Let's get back to the presentation, which is approaching to its end. So can you see my screen?
Yes, we can.
Okay, very well.
Yes.
Very well. Okay, so we even made this Q&A. So we are approaching the presentation to its end. Here is a list of those who already share our visions with us. So we hope others will come. Everybody is welcome in our project. We are one family with our clients, and the bigger we are, the stronger we are. So anyone is welcome. We believe TCFD is very affordable. I think it has the best value cost ratio in the market right now. So everybody is welcome. Feel free to contact us anytime, anywhere. We'll do our best to make you happy. Radek, I think it's time to say goodbye. Would you go for it?
Yeah. Thank you. So I would like just to thank you for watching, and I would like to add that this is just the beginning, because this new concept opened the door to another application to be more complex, to add quickly new features, to have a more complex workflow than previous version. So I think we all can look forward to new things, and we look forward for the cooperation with you and bring new nicer software to the market, and mainly to you. So thank you, and I'm really looking forward to cooperate.
Okay, thanks. It was perfect. It was extremely right. I have nothing else to say. So thank you. We leave you with that, and bye-bye for now.
Thank you. Bye-bye.
Bye.